Hi, I'm Davide, and today I'm going to present our work titled Understanding the Impact of Mistakes on Background Regions in crowd counting. Crowd counting is the task of counting people in images, and here we look at whether current approaches are good for real-world applications. Here we present some examples. On the left side we have the input image, and on the right side we have the predicted density map outputted by a state-of-the-art crowd counting approach. The count is then inferred from these predicted density maps. What we can see from these results is that the model is actually pretty good at localizing all the people in both images. However, when we look at the results on this specific image here from a metro station, we can see that the model outputs quite so many false positives or wrong predictions on the left side inside the red box, where the model mistakes some lights for people. Similarly, in this image the model mistakes some foliage and some stones for people and outputs a wrong count of 70. So in this paper we focus on this problem of mistakes on background and present an extensive quantitative analysis on it. Specifically, we focus on two questions. So how many mistakes are actually made, and can we help crowd counting networks not make these mistakes? We present our analysis on 6 datasets. 5 are popular crowd counting datasets, and 1 is a pure negative dataset that doesn't contain any person. We report mean absolute error, and we compute this on the full image, as classically done in the crowd counting literature, as well as on background and foreground independently. Note that background and foreground regions are not defined in any crowd counting datasets, and in our paper we present a simple technique to estimate this automatically. Here on the right side we have an example of an estimated foreground-background segmentation mask. Now, in the paper we present a lot of experiments and a deep analysis on the problem. But here, I'll focus at the main question. So how many mistakes are crowd counting approaches actually making? Well, if we look at the popular UCF QNRF, we can see that the number of mistakes on background are 42, which is actually quite a large number if we look at the foreground mistakes and we see there are only 94. Now, if you look at the word expo, this difference is even smaller, where the background mistakes almost equal the mistakes on foreground. So clearly, correcting these mistakes on the background is very important in order to further improve the performance of crowd counting and make it ready for real-world applications. Now, how can we actually help the network suppress these mistakes? Here we took a simple class like a crowd counting approach, which consists of a feature backbone and a regressor that outputs the density map, and then we equipped it with a segmentation head, which is trained to separate the foreground from the background. This is literally a segmentation branch. And then what we do is we use this outputted mask to modulate the original predicted density map and output a much finer, much cleaner output. Now, how much does this actually help? Here we present results on the 5 crowd counting datasets using CSRNet Plus as our baseline and equipping it with our background subtraction branch. The results show that the error on the background decreases on all datasets up to 43% on the GCC, showing indeed that we can help the network easily to suppress these mistakes. Interestingly, the error on the foreground also decreases. We conjecture that this is due to the regressor branch now being able to fully focus on the foreground, as the segmentation head is taking responsibility for the background. And improving background and foreground leads to an improvement on the full image as well. Now, we also run similar experiments where we evaluated on the 8820K negative data set, and you can see here that again, equipping our baseline with this background subtraction branch always reduces mistakes on background up to 83% using on the Shanghai Tech B. Now, how does this simple change relate to the latest advances of the literature in crowd counting? Well, it turns out that by focusing on just correcting the background mistakes, we can get results which are on par to the state-of-the-art on all the datasets that we evaluated on. Finally, please check our paper for much more experiments and evaluation. Thank you very much.